It's a function. Yeah. I didn't write this year, but so it could be whatever you think here. Okay.
It's not real.
But all this is a function that involves an exponential function, e to the power of something. And it actually is a kind of a chain of several functions. It's a composition of a couple things. So, I mean, the thinking here was that you would go through and do this algebraically and do it graphically. Like find the slope or the rate graphically and do it algebraically here. Okay? Like solve this analytically and graphically. I think we might leave this for now and come back to it because it's not a new concept, it's applying the concept.
Okay.
Do later. Later today or next class, okay? No, you gotta do it, but there's nothing new in this for me to show you. You go through and find the derivative of this and you can check between the graph and the algebra. I do want us to look at the other half of this, which is a natural logarithm function. I would like you to come up with the derivative of this. Guys, you can come up with the derivative of this using the instructions that are there. The instructions that are there. To do this, put it into exponential form and then do it implicitly. Okay? If it's something we don't know, because you know the derivative of e to the something, right? So if you change this to exponential form, okay, it means do the anti-ln of each side, right? E to the y equals x. E to the y equals x, right? And again, the way you do that is do the anti-logarithm base e, because this cancels out and you get that. Then differentiate implicitly with this, just the way we did, because this is like the inverse base e function, right? It's the same as we did with the trig functions. To do the inverse trig functions, we switched them around and did them implicitly. So we're switching this around and doing it implicitly. You'll come up with what the derivative is. You can always check that you're right by graphing what you get as your answer here, and then graphing, n deriv of ln x, right? Like that. The way we did before. You could graph it and see, right? You could graph that, and you could graph whatever you get as your answer here to see if you're right. Okay? Would it? Yeah, it would be the same. If whatever you get as your answer here, it's not good. This is not its own derivative. Okay, e to the x is its own derivative. There's not much else that it's its own derivative other than 0. Okay.
Which one? No.
Okay, if you want to check this for yourself, change it to exponential form. Differentiate both sides implicitly, or differentiate both sides with respect to x. On one side it's 1, right? The derivative of that is 1. The derivative of this is e to the y, but times y prime, or dy dx, whichever way you're writing it. So then to solve for y prime, or dy dx, you got to divide both sides by 1 over e to the y. And originally we knew that e to the y is equal to x. So you got the derivative is 1 over x. Now some of you are saying, is it only the positive part, or what's happening here? What's the domain of the original function here, that natural logarithm function? It's, x is greater than 0 here. So everywhere this function is defined, this works, right? When we go backwards, this one's actually defined in more places, right? The natural logarithm function looks like this, and the 1 over x function looks like something like this, and it's also over here. So you can say, if you want to know the derivative of this one, it's this graph. It doesn't matter that there's nothing over here because we don't need that, right? There's no x values over there. But when we go backwards later, when we do the antiderivative, okay, later on, when we do the antiderivative, you are going to have to use the absolute value, because when we say, what's the antiderivative of this, it's this, except it's going to be absolute value because you need the mirror image of it over here. Okay? So just store that away for now, and you'll see.
Okay, stored.
Store it away in your photographic memory. So this is something. And this is not anything new, it's just the chain rule. Now you should be able to do this in, how many minutes do you need to do this?
3 hours.
How many minutes do you need?
3 hours.
No. I can settle for 6. There it goes. You got 6 minutes.
I didn't do the last one.
I'll end this together, boys and girls. And, yeah.
Let's actually do one of these. Maybe you haven't done C, I'm not sure. C is easy?
They're all easy.
Well, I do want to do one here, so I have to write this one out anyway. So y prime is 1 over that thing times the derivative of what it is, 3. If you factor the bottom there and cancel it, you get 1 over x plus 1. Okay? If you factor out the 3 and cancel it. They're all I think they're all kind of easy enough if you look at it. This one you need the product rule because it's a product, x times ln x. This one is a chain rule thing because it's a composition, ln of ln x.